Hello everyone, I welcome you all to Startup Academy, your online gateway to get success in ISS exam. This academy is exclusively for ISS and we have been doing the topic time series analysis, in that also advanced time series. In the previous lecture, we were discussing about spectral density function of AR autoregressive model of order 1. The spectral density function, I am writing it as SDF of AR1, which we calculated in the previous class, came out to be F lambda equals to 1 upon 2 pi into sigma square upon 1 plus phi square minus 2 phi cos lambda. This was our spectral density function for AR model 1. Now we'll draw the graph. For before that, I want you to know if phi reaches to 1, then spectral density function becomes f lambda equals to 1 upon 2 pi, and phi reaches to 1, it is sigma square upon 1 plus 1 minus 2 cos lambda, which is nothing but 1 upon 4 pi sigma square upon 1 minus cos lambda. This is the spectral density function of random walk model. So if an exam they ask you about what are the spectral density function of random walk model, then we'll first find out autoregressive model of order 1, and then by putting phi reaches to 1, limit of phi reaches to 1, we can find the spectral density function of random walk model. Now we have to draw two graphs of spectral density f lambda with respect to lambda. Now if these are the two values where sigma square upon 2 pi and 1 minus phi square, sigma square upon 2 pi 1 plus phi square. First let me draw, then I will explain. F lambda and lambda, sigma square upon 2 pi 1 plus phi square and sigma square upon 2 pi 1 minus phi square. So this is when phi is greater than 0, and this is when phi is less than 0. When phi is greater than 0, then there is where the explanation would be when phi is greater than 0, then covariance function is positive. There is a positive autocovariance function, hence we can say that the this what do we call this? This is spectrum. This spectrum is dominated by low frequency and hence smooth curve. And for this, when phi is less than 0, then autocovariance function is negative and spectrum is dominated by high frequency and therefore rough curve. So these are the curve of AR model 1, where phi is greater than 0 and phi is less than 1. When phi reaches to 1, I've told you it is random walk model, and the other two cases are here. Now in today's lecture, we'll discuss about moving average. Spectral density function of moving average model of order 1. Now we know that the moving average model of order 1 can be written as xt equals to theta wt minus 1 plus wt. For all wt are white noise and with mean 0 and variance sigma w square. Okay, so this is our model. Now again we'll find I'm finding the covariance between x t plus h and xt, which can be found out by covariance. This is autocovariance of order of lag h. So covariance of x t plus h is w t plus h minus 1 plus w t plus h theta w t minus 1 plus theta plus w t. If we find the covariance between them, we'll find that it is nothing but theta square covariance between w t plus h. This is the formula. Now if we take h equals to 0, then rho h or rho 0 will be, gamma 0 would be, or autocovariance with lag 0 would be 1 plus theta square into sigma square w. This we have done in moving average model, the direct estimate. I'm writing the direct result. If you are confused with the result, then you can rewatch that previous video. And for h equals to plus or minus 1, then gamma 1 would be gamma minus 1 equals to theta sigma w square. And for h greater than equal to 2, then gamma h would be equal to 0. So this was the autocovariance function. I'm writing the direct results, and now we'll find out the spectral density function. We know that spectral density can be written as f lambda equals to 1 upon 2 pi gamma naught plus summation h goes from 1 to infinity 2 times e raised to the power gamma h into e raised to the power minus I h lambda. Now we can just simply replace the value. Here it is 1 plus theta square into sigma w square plus 2 into summation h goes from 1 to infinity cos h lambda. This I e raised to the power minus h lambda can be converted to cos h lambda, and gamma h is nothing but theta sigma w square. Taking the common things outside, sigma w square upon 2 pi, we are left with 1 plus theta square plus 2 theta summation h goes from 1 to infinity cos h lambda. So this is our value for f lambda of or spectral density function, where lambda goes from minus pi to pi. So this is the value for spectral density function of moving average of order 1. Likewise, this you can find of moving average q, and like we did for autoregressive model of order 1, Likewise that you can do for autoregressive model for order P. That's your homework. Now the graph of this. The graphs are similar if lambda and lambda. If lambda, this is sigma square upon 2 pi into 1 plus theta square, sigma square upon 2 pi into 1 minus theta square. So this would be again like this, and this is for theta greater than 0. And again the second graph would be like this only. Lambda, f lambda, sigma square upon 2 pi into 1 minus theta square, sigma square upon 2 pi into 1 plus theta square. And the graph would be like this for theta less than 0. Here also low frequency dominated by high frequency, and and one more thing was there, it is dominated by low frequency. Smooth curve and rough curve. That these are the two graphs that we need to draw in the exam for moving average model of order 1. Now moving forward, there is one more thing which is known as the normalized form of spectral density function. Normalized form of spectral density function. Now we know that the spectral density function of any function can be determined as 1 by 2 pi gamma naught plus 2 into summation h goes from 1 to infinity e raised to the power minus I lambda h and gamma h. We can write it like this. So this is how we define our spectral density function. The normalized spectral density function can be defined as it is just simple, we have to just divide. If the normal spectral density function is f star lambda, then it can be defined as if we divide the spectral density function with autocovariance function of lag order 0 or variance, so anything you can say. So this would be our normalized form of spectral density function. So if we divide this, f lambda upon gamma naught equals to, this was 1 upon 2 pi gamma naught upon gamma naught plus 2 into summation h goes from 1 to infinity e raised to the power minus I h lambda gamma h upon gamma naught. Now this can be restated as f star lambda, which is the normalized form of spectral density function, 1 upon 2 pi. These are same, so it would be 1, and 2 into summation h goes from 1 to infinity e raised to the power minus I h lambda, and this ratio we have already done. It is nothing but autocorrelation function of lag order h. which is represented by rho h. So this is our value of normalized spectral density function. Okay. So this completes, and it is also known as the Fourier transformation of autocorrelation function. This definition I made you do in the first class of this spectral density function. There you couldn't understand it. So now I hope that it is understandable why I said that it is the Fourier transformation of autocorrelation function, because Fourier transformation means conversion of sines and cosines, sum of sines and cosines. So here sine is negative. Here this e raised to the power minus h lambda, e raised to the power minus I h lambda can be written as cos h lambda plus I sine h lambda, and e raised to the power minus I h lambda can be written as cos h lambda minus I sine h lambda. Now, and I is nothing but under root of minus 1, which is imaginary number. And this becomes 0 because it is an odd function. Therefore, we just take cos here. So, here this also can be written as cos h lambda, which is the Fourier transformation of autocorrelation function, which is this autocorrelation function. And hence the definition that the spectral density function is the Fourier transformation of the autocorrelation function. That's it for today. I hope that whatever we have done in the class is clear with all of you. If not, then you can ask in the comment section or on WhatsApp channel. Only relevant doubts will be answered. And if you are facing any issues, then you can rewatch the videos in which I have explained in details all the concepts. And if you still face any doubts, then we are available for you to clear all your doubts. All the best. Thank you.